Alright, what are you doing?
What am I doing? I'm doing physics.
Welcome to Flip Physics. Today I'm going to talk about magnetic forces. In our last video I introduced what magnets are and a few basic facts about them. Now it's time to be a little bit more specific. Just how strong is the magnetic force? And how can we make it weaker or stronger and use that to our advantage in a machine like this MRI scanner? Magnets have fairly limited uses. It's really just about as strong as it is, and we can't turn it off or on. But as I said in my last video, magnetic fields are produced by moving charges. So if we can move electrons around an electrical circuit, we can produce a magnetic field. This is called an electromagnet. They tend to be wound up in coils like this. With an electromagnet, you can turn it off. You can turn it on. You can change the strength of it by increasing or decreasing the current flowing through the wire. And by having this nice controlled environment, we can very easily come up with an equation for the magnetic force produced by such a wire. And here it is. B is the magnetic field strength measured in Teslas. Mu is a constant called the permeability of free space, otherwise known as the vacuum permeability. I is the current flowing through the wire, measured in coulombs per second or amps. It's just the amount of charge flowing past a point in the circuit per second. And R is the distance or radius from the wire. So that's how we figure out the magnitude, the size of the magnetic field produced by a wire. But magnetic field is a vector, so how do we figure out the direction of the magnetic field? For that, you need to use
the first right-hand rule.
So now I want everybody to give me a thumbs up. Absolutely everybody. I know you're not doing it, put your thumb up, point it towards me, every single one of you. Alright, so once you've got your thumb pointed up like this, now I want you to point your thumb in the direction of the current flowing through this wire. So you can move around like this and point it however you want, so point it in the direction that the current is flowing through the wire, the current marked by the arrow. Now imagine yourself grabbing the wire, curling your fingers around the wire, keeping your thumb in that same direction. The direction your fingers point, the direction your fingers curl, tell you the direction of the magnetic field around that wire. So it looks something like this. Circles around the wire pointing in the direction that your fingers point. Make sure you always use your right hand. That's why it's called the right hand rule. If you use your left hand, your answer will be exactly wrong. Now, physicists don't tend to be the best artists, and so we don't necessarily want to draw in 3D like this. So there's another way to draw this. Imagine for a second that you're being attacked by angry physics gnomes. So click here if you don't know what an angry physics gnome is. So anyway, angry physics gnomes usually attack with bows and arrows. They're fairly old-fashioned that way. If an angry physics gnome fires an arrow straight at you, what's the first thing that you see? You see the point of the arrow coming towards you. So a dot represents an arrow coming towards you, or in this case a magnetic field coming towards you. What does the gnome see as that arrow moves away from him? Well, arrows have feathers on the back, so if you fire an arrow, you'll see the feathers moving away from you. So a cross represents an arrow moving directly away. So a dot is out of the page, a cross means into the page. So this field that we drew in 3D could also be represented like this, just makes drawing it a lot easier. And again, if you imagine trying to grab the wire, your fingers will go into the page on one side and out of the page on the other side. So that's how you figure out the field created by a current carrying wire. Both the magnitude using the equation and the direction using the right hand rule. The next thing we need to talk about is what happens when two magnetic fields interact. If you overlap two magnetic fields, they interact and strange things start to happen. The upshot is if you take a charge and move it inside an external magnetic field, a magnetic field created by something else, like a big bar magnet or something external to the charge itself, that moving charge will feel a force due to that external magnetic field. So that could be an individual electron moving between the poles of a bar magnet. Or it could be an electric current, charges flowing around the wire. It doesn't matter whether those charges are inside a wire or outside of a wire. If they're moving inside an external magnetic field, the charges will feel a force. Either the individual charge or the wire itself will feel a force. If it's a wire, you calculate the size of that force using this equation, where F is the force felt in newtons, B is the strength of the external magnetic field, I is the current flowing through the wire, L is the length of wire that's inside that field, theta is the angle between the field and the current, which is usually 90 degrees. Sine 90 is 1, so then you can just kind of ignore that part of the equation. It's very important to be super clear about the fact that the B in this equation is the external magnetic field. The wire itself will produce its own magnetic field, but that's a different magnetic field. We're talking about maybe a wire being put near a bigger magnet that's producing its own field. The wire can't apply a force to itself. The field that causes the force has to come from outside somewhere. Now, if instead of charges flowing in a wire, you have an individual charge like a proton or an electron, and that proton or electron is what's moving inside the external magnetic field, you no longer have a current, but you can instead use this equation to calculate the force on that charge. Here, Q is the charge of the moving particle measured in coulombs, V is the velocity of that particle as it moves through the field, B is again the strength of the external field, and theta is the angle between the velocity and the field. Again, in most cases that's going to be 90 degrees. So that's how you calculate the magnitudes, but again, force is a vector quantity, so how do you figure out the direction? Here is where we introduce our second and third
Right-hand rules.
The first one was like that, but the second one and third one look very different. I want you to make this shape. Notice that all three of my fingers, my thumb and my two fingers, are pointed at 90 degrees to each other. That's 90, it's all 90. So I've got my thumb pointed straight up, my pointing finger pointed forward like a gun, and my middle finger pointed off to my left as I pointed out. And I'm using my right hand because it's a right hand rule. When you make the shape, the thumb represents the direction that the charges are moving, whether that's the current in the wire or the individual charge. Your pointing finger, that represents the direction that the magnetic field is going. And if you get those two fingers in the right orientation, then your middle finger will represent the force that the wire will feel due to that motion. So here's an example. Point your thumb in the direction of the current, point your pointing finger in the direction of the magnetic field, which is kind of like that, and then your middle finger will show you which direction the force on this wire will be. So this wire, positioned as shown in the diagram, will feel a force directly up. So that's the second right-hand rule. The third right-hand rule is almost exactly the same as the second, except your thumb, instead of representing the direction that the current flows, is now representing the direction that the individual charges are moving. So the third right-hand rule is where we have individual charges moving inside a magnetic field. But everything else is the same. You point your thumb in the direction the charge is moving, you point your pointing finger in the direction the field is pointing, and your middle finger tells you the force. So here, for example, the particle is moving directly up, so you point your thumb directly up. The field is going this direction, so you point your finger this direction, and then that tells you your force is that way. I'll point out for these right-hand rule problems that you do have shoulders, and you do have elbows. Just saying. You wouldn't think I would need to say that, but I really do. So one last important note. With those last two right-hand rules, you use your right hand for conventional current and positive individual charges. An individual charge like a proton moving. If you have an electron or another type of negative charge, you switch to your left hand and do the same thing. That's the only time that you use your left hand, when a negative charge is moving. And that's because the force on a negative charge will be in exactly the opposite direction. Okay, boys and girls, now it's story time. The right-hand rule fingers can be hard to remember, so hopefully this story will help. One day while you're driving down the street, you see lots of different things. The first thing you see is a hitchhiker. What do hitchhikers do? They go like this, and they point their thumb in the direction that they want to go. So you make a thumbs up, and your thumb represents the direction of motion. So you don't really want to pick up a hitchhiker, so you keep driving down the street, and the next thing you see is a bunch of kids, and the kids are playing either cowboys and Indians or cops and robbers, something like that. What do the kids do when they play that? They go pew 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 pew. They make banging noises. B for bang, B for B field. So your pointing finger is the direction of the B field, of the magnetic field. You drive a little bit further and then someone cuts you off. You get really angry and you say, "Get the force out of my way." And so your middle finger is your force finger. F for force. Please note that flip physics in no way condones making rude gestures to other drivers. Such acts are infantile, dangerous, and may result in decapitation. They may. It's possible. Shh. So there you have it. You now have 3 equations and 3 right-hand rules. An equation to tell you the field created by a current-carrying wire and the direction that field points. An equation to tell you the force that a current-carrying wire will feel inside an external, outside magnetic field. And a right-hand rule to tell you the direction that force will have. And lastly, an equation to tell you the force that an individual moving charged particle will have inside an external magnetic field. And a right-hand rule to tell you the direction that force has. And after watching this video, if you're ever in one of those really huge exam halls with lots of people taking various exams, you'll always know who is taking the physics exam. They'll be the crazy looking ones going like this as they try to desperately contort their wrist into the right orientation for the question. Hopefully if you use your shoulders and elbows you won't look quite so silly. But I mean, no promises or anything. Thanks for watching Flip Physics. If you like this video, you can press the like button, you can also subscribe, or go to the flipphysics.net website. But most of all, don't forget to leave a comment below with your questions, thoughts and suggestions. Until next time, keep questioning.